AB Calculus 2.2, Definition of Limits. Essential learnings for this video are finding limits from graphs and tables, one-sided limits, the existence of limits, and the greatest integer function. So a preliminary definition of limits, or the limit of a function. Suppose the function f is defined for all x near some value a, except possibly at a. If f of x is arbitrarily close, meaning as close to L as we would like, for all x sufficiently close but not equal to a, we write that the limit as x approaches a, so limit as x approaches a of f of x equals L. We say that the limit of f of x as x approaches a equals L, as we just said. This just means that the graph approaches a value L as the graph approaches a particular x value. So L is just a y value, an output, where a is an x value. We'll explain here as we go. That's just the preliminary definition. So let's first look at example 1 and find the following values using the graph of y equals f of x. Okay, so f of 0, well, we find 0 on our x-axis, and we find the output that coordinates with 0 as an input. So f of 0, as we know here, would be 1. Now f of 3, well, where's x equals 3? Here it is. F of 3 is not 0. This is called a removable discontinuity, or a discontinuity in the graph. Therefore, f of 3 is negative 1. Okay, let's look at a second example. Consider the function g of t equal to t squared minus 9 over t minus 3. Complete the table, and then let's approximate what we think the limit would be as t approaches 3 of g of t. Okay, so let's plug in a 0. Well, g of 0 would be 0 squared minus 9 over 0 minus 3. So it looks like t of 0 is 3. Let's try t of 6. 6 squared minus 9 over 6 minus 3. Well, that's 36 minus 9, which is 27. 27 divided by 3 is 9. Okay, let's go g of 1. 1 squared minus 9 over 1 minus 3. Well, it's going to be negative 8 over negative 2, which is 4. But g of 5, that'll be 5 squared minus 9 over 5 minus 3. 25 minus 9, which is 16, over 2, which is 8. G of 2 is 2 squared minus 9 over 2 minus 3, which will be negative 5 over negative 1, which is 5. And g of 4 will be 4 squared minus 9 over 4 minus 3, which comes out to be 16 minus 9, which is 7 over 1, which is 7. Okay, so go look at that. We got 3, 4, 5, something, 7, 8, 9. Well, my best guess would be that our limit here is going to be 6. Now, this is not necessarily the output at 3. So let's find out what the actual output is. I'm fairly confident that our limit as t approaches 3 of g of t is 6. However, what's the output? So g of 3. Well, g of 3 would be 3 squared minus 9 over 3 minus 3. And from here on out, anytime you see an output of 0 over 0, you should always think there's more than meets the eye. Okay, so that is an indicator that you got more work you need to do. Okay, however, you should be able to see that when we calculate this limit from the left and the limit from the right, it makes sense that the function is approaching 6 from both sides. Okay, let's look at some more examples. One-sided limits. The limits we just calculated are called two-sided limits because the function approaches a value L. In the case of the other problem, we were approaching 6 when x was greater than 3 and when x was less than 3. For some functions, we'll need to talk about one-sided limits. So a right-handed or right-sided limit with this notation. The limit as x approaches a from the right of f of x, and the limit as x approaches a from the left of f of x. That's a left-sided or left-handed limit. So let's look at these in action. Example 3. Using the graph shown for y equals f of x, evaluate the following one-sided limits. So let's use this graph. Evaluate these limits. So the limit as x approaches -1 from the left of f of x. So as I approach -1 from the left, what's my output there? It's going to be 0. Okay, what about -1 from the right? Well, it looks like my limit there is going to be -1. Right, so what about the next example? The limit as x approaches 1 from the left. The limit as x approaches 1 from the left would be here. Looks like it's going to be 1. The limit as x approaches 1 from the right. As we approach x equals 1 from the right, looks like our output is 2. What about if we approach 2 from the left? 2 from the left is -1, and 2 from the right, that limit is +1. Okay, let's continue and see how this applies to the rest of our topics. Okay, so the existence of a limit. Assume that f is defined for all x near a except possibly at a. Then the limit as x approaches a of f of x equals L if and only if the limit coming from the left of a of f of x equals L and the limit as x approaches a from the right of f of x equals L. That means that the left-sided limit and the right-sided limit, they have to agree. Okay, so let's look here. Let's find these first values. F of -4. Well, f of -4 looks to be, doesn't exist. Let's see here. Does not exist, right? We can see that here, f of -4 is nowhere to be found. Okay, how about f of 1? F of 1 is 4. And f of 6 is 2. All right, now let's look at some left-handed, right-handed limits. Okay, let's go back to x equals -4. And from the left of -4, looks like our limit is 2. From the right of -4, looks like our limit is 2. Since those two limits agree, then the limit as x approaches -4 of f of x is also 2. Okay, let's look at x around 1. As we approach 1 from the left, looks like our limit is 4. As we approach 1 from the right, our limit or our output is approaching -2. Since those two do not agree, then the limit as x approaches 1 of f of x does not exist. Okay, let's look at the function f of x close to x equals 6. I see that the left-sided limit and the right-sided limit are going to agree. They're both going to be 5. Therefore, the limit as x approaches 6 of f of x will also equal 5, even though the actual output for f of 6 equals 2. Okay, let's continue on with this topic on the next slide. Okay, here we have a new function, one that you've probably not seen. It's called the greatest integer function. Here's the notation for the greatest integer function. That's f of x equals the greatest integer function. This is sometimes also called the floor function. The y value will always be the largest integer that is less than or equal to the x value. So let's sketch the greatest integer function. And let's go with just a couple of intervals of the greatest integer function. Okay, so any value, say for example, f of 0.3, that will round to the next integer that is less than or equal to x, or 0.3, which will be 0. What about f of 0.7? That will also map to 0. What about f of 1? Well, that'll map to the nearest integer less than or equal, which will be 1. What about f of 1.99? That would also map down to 1. So what the greatest integer function will look like is a set of steps. So let me use a different color here. Let's go red. Any number less than or equal to, greater than or equal to 0 and less than 1 will map to 0. Any number that is greater than or equal to 1 and less than 2 will round down to 0, or excuse me, to 1. Any number here that is greater than or equal to -1 and less than 0 goes to -1, and you can see how the pattern will continue. Okay, so what happens when x gets near 2? Okay, so let me sketch this out. What can we say about the limit? Well, let's look at the limit from both sides of 2. So the limit as x approaches 2 from the left of this function called the greatest integer function. Well, as we approach from the left, looks like it equals 1. As we approach from the right, that limit will equal 2. So the limit will never exist at any integer value. Now the limit will exist between integer values, but not at any integer value on the greatest integer function. So with that being said, for a limit to exist, the function must approach the same value from both sides. To find a limit of a function, you must check the value from both sides of that x-coordinate. All right, let's continue. Apparently there's no more slides, so that'll be it for today. That is 2.2 on one-sided, two-sided limits, the existence of limits, and the greatest integer function. See you in the next video.